Hello dear friends, we are going to study now the modified counters part 2. In this one, we are going to study the mod 6 counter. Last time, you have studied the basic how the modulus of the counter can be changed, and you have also studied about mode 3 counter which can be prepared from two flip-flops, because with the two flip-flops natural count is 2 raised to 2, that is equal to 4. So, skipping one of the state, we can convert a natural counter of mode 4 counter into mode 3 counter, which is having three different state. It is having 0 0, 0 1, 1 0, and the next step 1 1 was skipped, and that way it was reset to again 0 0 after 1 0. And that way we have converted mode 4 counter into the mode 3 counter. Now, that mode 3 counter we can utilize is a basic building block, and higher models of the counter can be prepared. How? Let us see here. If we consider a basic flip-flop to be mode 2 counter, we see that mode 4 counter is nothing but two flip-flops are connected in series. If the flip-flops are utilized, a single flip-flop is going to be utilized when J and K is connected to the VCC. That means J is equal to K is equal to 1, and when the clock pulse is applied to the flip-flop, then if it is JK flip-flop and negative is triggered, or if it is a master slave flip-flop, then it will change the state on negative transition of the clock pulse, and output of the flip-flop is storing either 0 or 1, or it is going to be toggling mode, and that way it is working as a mode 2 counter. So, if there are two flip-flops are going to be utilized, that means it is working as a 2 multiplied by 2, that is going to be two flip-flops are connected in series, and that way mode 4 counter can be prepared. Similarly, if there are three flip-flops are connected in series like this way, mode 2 counter into mode 2 counter into mode 2 counter, that means 2 multiplied by 2 multiplied by 2, that is going to be mode 8 counter can be prepared. What it indicates? This indicates that thus a great number of higher modules of the counters can be formed by using the product of any number of lower modules of the counter. That means if you want to prepare a higher modules of counter of your desire, then you have to connect so many lower modules of the counter in a proper way, so that you can generate a higher modules of counter by connecting them in a series mode. Let us consider now mode 6 counter. How mode 6 counter can be prepared? We need a two type of the counter. One is mode 3 counter we require. Another one is the single flip-flop, which is a mode 2 counter. We can connect this 2 counter in two different ways. Either the mode 3 counter is followed by mode 2 counter, which is known as a 3 by 2 counter, and that way mode 6 counter can be prepared. Or if we put a mode 2 counter or flip-flop in front of mode 3 counter, that means mode 2 counter, which is going to be followed by mode 3 counter, and that way also 2 by 3 mode 6 counter can be prepared. When we are doing this thing, what is happening about the waveforms? How many discrete states are going to be there, etc. we are going to study. So first we are going to study about mode 6 counter, which is nothing but mode 3 counter, which is going to be followed by mode 2 counter. So for this instance, suppose that we connect a flip-flop at the B output of mode 3 counter as shown in the figure. You can see this figure. Here, this is a logic diagram or block diagram. We are utilizing mode 3 counter as a logic building block, and higher modules of the counter is to be prepared. So this is a mode 3 counter, which is followed by mode 2 counter by a single flip-flop. So output of the mode 3 counter, that is the output of B, because mode 3 counter A is the LSB and B is going to be MSB. This MSB is connected as a clock input to the flip-flop C. This we can designate or we can label. This is the flip-flop C is going to be there, and its J and K connection is connected to the VCC. So it is going to be toggle on every negative edge of output of the B waveforms. That you can visualize in this waveform also, that is shown in a B figure. Here you can see that this is the clock waveforms. This is the clock waveforms is running. So this is the clock is applied to the mode 3 counter. So first output of A and B we can draw for the mode 3 counter. You can see that initially all the flip-flops were reset. It means A is equal to 0, B is equal to 0, and C is equal to 0 prior to the first clock age arrived. When the first clock age is going to be arrived, the first flip-flop A is going to be toggle. So A is changing from 0 to 1, B remains reset, and on the second clock pulse, when the second clock pulse is there, A is also going to be toggle and B is also going to be toggle. And on the third clock pulse, B is going to be reset, and that way this counter is progressing from B is equal to 0, A is equal to 0, B is equal to 0, A is equal to 1, B is equal to 1, A is equal to 0, and then again it is going to be reset 0 0 condition, and again the sequence is going to be repeating. That is 0 1 1 0 and 0 0, 0 1 1 0 and then 0 0 with the clock pulses. So this way A and B is the waveform for mode 3 counter is shown over here. Output of P is connected to the clock input for the flip-flop C. So when the output of P is making a transition from high to low, the flip-flop C is going to be toggle. So you can see that until this point, C remains reset. At this point, when output of B is going to be changing from high to low, the flip-flop C is going to be toggle. Again, that second time, when B makes the transition from high to low, C is going to be toggle here. Again, when the B makes the transition from high to low, C is going to be toggle. Now, this is the waveform. Now, what will be the truth table from here? C is going to be the MSB and A is going to be LSB. So, C, B, A will be there. On a 0 count, 0 0 0 condition is going to be there. On a first count, 0 0 1 will be there. On a second count, 0 1 0 will be there. On a third count, 1 0 0 0 will be there. On a next count, it is going to be 1 0 1 will be there. On the next count, 1 1 0 will be there, and again it is going to be repeating 0 0 0. That means this counter is progressing through 6 discrete states, and then after the sequence is going to be repeating. And this way, this will result a 3 by 2 mode 6 counter. That's why it is known as the mode 6 counter, because this counter undergoes 6 different discrete states, and then it is going to be repeating the sequence. The output of the single flip-flop C is labeled as a C. Notice that it is a symmetrical waveforms, and it is also has a frequency of 1/6 that of the input clock pulse. You can see that. What is the how many waveforms are going to be accommodated of the clock in one single output of C waveforms? If you consider that C waveform is going to be starting from here, then this is going to be clock 1, 2, 3, 4, 5, and 6. So 6 period of the clock waveform is equal to 1 period of the output waveform of flip-flop C will be there. When it is going to be low and it is going to be high, this complete 1 clock pulse. Or you can start from here when it is going to be high and it is going to be low. This you can see that starting from here. 1 clock pulse, second clock pulse, third clock pulse, fourth clock pulse, 5 clock pulse, and 6 clock pulse. That means the period of 6 clock pulse is equal to period of one clock pulse of the C waveform. So the periodic time of C is equal to 6 times the periodic time of the clock waveform. So the frequency is divided by 1 upon 6. So the waveform is said to be 1 upon 6 that of clock waveform. So this is called divide by 6 counter also. Also, this can no longer be considered as a synchronous counter since the flip-flop C is triggered by the flip-flop B. So all the flip-flops are not changing the state in synchronism with the clock because clock is given to first and second flip-flop A and B only directly, and output of B is acting like a clock for the flip-flop C. So all the three flip-flops are not changing the state in synchronism, and hence it is not considered to be synchronous counter. It can be considered as asynchronous counter. And because of that, there may be possibility that glitches can occur output of decoding gates. The flip-flop do not all change its state in synchronism with the clock pulse. Now, the next counter which we are going to see, again it is a mode 6 counter, but slightly different way. Here it is 2 by 3, that is going to be mode 6 counter will be there. How it can be prepared? Initially, we are going to utilize here the flip-flop, that is mode 2 counter is going to be there. The J and K is connected to the VCC and its output is connected to the clock input of mode 3 counter. And that way 2 by 3, this is also a mode 6 counter. But working of this one is going to be different. That you can see through the waveforms. Draw the waveform you would expect from a mode 6 counter by connecting a single flip-flop in front of mode 3 counter as shown in the figure 310.16. Solution. The resulting counter is 2 by 3, which is known as the mode 6 counter that has the waveform shown in the figure 10.80. Notice that B now has a period equal to 6 clock pulse periods, but it is not symmetrical. Previous waveform it was symmetrical, but this waveform are not going to be symmetrical waveforms. Now you can draw the waveforms like this one. This is your clock waveforms. Perfectly periodic waveforms are going to be there. That means it is going to be high. Then when it is changing the state from high to low, the flip-flop is going to be triggered because these flip-flops are negative age trigger and output is going to be toggle. Every time there is the negative transition of the clock pulse, the flip-flop output is going to be changes or it is going to be toggle. Let us consider this flip-flop is Q. So here initially all the flip-flops were reset. So Q, A and B were reset. Here B is going to be the MSB and Q is going to be the LSB will be there because the clock pulse is given to this first flip-flop and its output is going to be LSB. And the last flip-flop which is changing the state is going to be B, and that's why it is said to be MSB. So when negative age of the clock will occur, the output of Q is going to be toggle every time. Again here the negative transition will be there. Again the Q is going to be toggle from high to low. Again at this negative clock transition, third clock pulse, it is going to be changing. At the fourth clock pulse, it is changing. Fifth clock pulse is going to be changing, and so on. So this is the waveform of output of Q waveform, that is Q flip-flops. And this output is working as a clock input for the mode 3 counter. That means it will drive both the flip-flops A and B, that this clock pulses will be utilized as a clock input for the flip-flop A and B, and that is a synchronous counter. So now what happens? This is a mode 3 counter. You can think about that instead of this waveforms, this is the clock waveform for the mode 3 counter, and output of this mode 3 counter is A and B. So initially A and B was reset. So when the first negative age of the clock pulse occur, the output of the flip-flop A is going to be toggle. but B remains reset. Then on the second negative edge of the clock pulse, that is output of Q, when makes a transition from high to low, A is also going to be toggle and B is also going to be changes, or it is going to be toggle. That means A makes a transition from high to low and B makes a transition from low to high. Again, when the third negative edge of the clock pulse, that means here, A remains reset and B is going to be reset. That means this is also going to be 0, changes from high to low, and it is going to be reset. So after 3 clock pulse, output of A is also going to be reset and B is also going to be reset. Again, on the 4th clock pulse, A is going to be set, or it is going to toggle. On a 5th clock pulse, A is going to be toggle and B is also going to be toggle. On a 6th clock pulse, A is going to be reset and B is also going to be reset, and that way this sequence is going to be complete. Now see the waveform of A and B. A and B are almost identical waveforms, but here there are two waveforms of the periodic time 2 clock pulses. It remains high, but for the 4 clock pulses, it remains to be in a low state. That means time for which this output of A or B remains high and time for which it remains high or low, that is going to be different. And that's why it is known as a asymmetrical waveforms. And but the modulus of this counter is going to be the same because it is passing through the 6 discrete state, and then the sequence is going to be repeat. That's why it is known as a mod 6 counter. What is the truth table? If you want to prepare the truth table from the waveform, you can prepare. On a count 0, that means before the clock pulse occurs, B is equal to 0, A is equal to 0, and Q is equal to 0. On a count 1, B is equal to 0, A is equal to 0, and Q is equal to 1. On a count 2, B is equal to 0, A is equal to 1, and Q is equal to 0. On a count 3, B is equal to 0, A is equal to 1, and Q is equal to 1. On a count 4, B is equal to 1, A is equal to 0, and Q is equal to 0. On a count 5, B is equal to 1, A is equal to 0, and Q is equal to 0. On a next count, that is count 6, this is going to be 0, this is going to be 0, and this is going to be 0. That means it is progressing from 0, 0, 0 to 1, 0, 1, 6 different states, but strictly in a binary sequence. And that way, this will work as a modulus of 6 counter. Now, we are not going to prepare this kind of counter externally, but we are going to utilize the IC which is already available in TTL family. That is IC is 547492A. This IC is known as normally 92A. This is a TTL divided by 12 counter, MSI counter. This IC is named as a divided by 12. MSI counter is from there. In this IC, you can use as a mode 6 counter also, and you can use as a mode 12 counter also. How it can be done? If you see the waveforms, then you can find out. This is the schematic circuit diagram of the IC inside. How many flip-flops are there? There is one flip-flop that is known as the A flip-flop, J and K. Output of this flip-flop is going to be QA. This is nowhere connected. This is simply isolated. Here, there are other 3 flip-flops are going to be there. Flip-flop B, flip-flop C, and flip-flop D. These 3 flip-flops are connected in such a way that it is making a 3 by 2 counter, that is a mode 6 counter. That means if you want to operate these flip-flops, that is QB, QC, and QD only, and you give the system clock to the clock input B, because there are 2 clock inputs, clock input A and clock input B. So if you give the system clock to the clock input B, we are not utilizing the flip-flop A. We are utilizing only these 3 flip-flops. Now QD is going to be MSB and QB is going to be LSB. So, and this is going to be mode 3 counter, which is followed by mode 2 counter. and that way it is working as a 3/2 counter. And when you give the clock pulse, this container of the counter is going to be incremented from 000 to 3/2 counter to table it will follow, and then it is going to be repeat. So this way you can utilize as a mode 6 counter. But suppose you want to prepare a mode 12 counter, then what you are supposed to do? You have to apply the clock pulse or system clock to the input A. Here, the system clock is applied at the input A, pin number 14, and output of QA is connected as a clock input to the flip-flop T. Then this output wire is connected here. That means it is working as a modulus of 2 counter, which is going to be followed by modulus of 3 counter, which is going to be followed by modulus of 2 counter. That means 2 multiplied by 3 multiplied by 2, and that way it is working as a modulus of 12 counter. This is that IC. You can see that in this IC, pin number 5 is a VCC. Because this is a TTL IC, you have to apply plus 5 volt regulated power supply. Pin number 10 is supposed to be the ground. Pin number 1 is the clock input B is there. You see that it is negative is trigger. Pin number 14 is also clock input, but it is clock input A will be there. Pin number 2, pin number 3 and pin number 4 NC. NC means no connection. They are not utilized. They are unused pins. R01 and R02, they are controls for resetting all the flip-flops. You can see that how it is connected to the NAND gate. R01 and R02 are the input of the NAND gate, pin number 6 and pin number 7 of this IC. So, when R01 and R02 are going to be high, what will be the output of the NAND gate? Both the inputs of the NAND gate is going to be high, output of the NAND gate is going to be low. And when it is going to be low, that means all the flip-flops, this terminal, which is nothing but the clear terminal or reset terminal, this is connected here, this is also connected here, this is also connected here, and this is also connected here. That means when both R01 and R02 are going to be high, output of the NAND gate is going to be 0. That means all the flip-flop clear terminal is going to be activated, and all the flip-flops output is going to be clear, or it is going to be reset. That means QA is going to be 0, QB is going to be 0, QC is going to be 0, and QD is going to be 0. This is the work function of these two controls. This means 12 number is QA output, 11 number is QB output, 9 number is a QC output, and 8 number is a QD output. These are the outputs. So, this IC, when you are utilizing as a 2 multiplied by 3 multiplied by 2, then this will show the truth table how it is working. QD is going to be the MSB, then QC, then QB, and QA is going to be the LSB. Prior to the clock pulses, all the flip-flops are going to be reset, so it is going to be shown by LLLA, that means low, and H stands for high. So on the first clock pulse 0001, on the second clock pulse 0010, on a third clock pulse 0011, fourth clock pulse 0100, fifth clock pulse 101, on a sixth clock pulse it is going to be 1000. That means it is not now progressing strictly in a binary sequence. Up to this it was in a binary sequence, then it is changing, you can see that. From state number, this decimal equivalent of this one is going to be 5, then directly it is moving to the state number 8, that means 1000, that means decimal number is going to be 8. This is going to be 9, 10, 11, 12 and 13, but the total number of state through which this counter is going to be progressing is going to be 12 only, 0 to 11, and again it is going to be reset to 0. That is why it is working as a modulus of 12 counter, which is everything is going to be written over here. You can see that careful examination of the logic diagram will reveal that the flip-flop QB, QC and QD are exactly the same as 3 by 2 counter in figure 10.17. Thus, if the clock is applied to the B input of 92A and the output are taken QB, QSC and QD, this is working as a mode 6 counter only. On the other hand, if the clock is applied at input A and QA is connected to the input B, we have a 2 multiplied by 3 multiplied by 2, a mode 12 counter. The proper truth table for this mode 12 configuration is given in figure 10.19b. Again, this must be considered as a asynchronous counter since all the flip-flop do not changes the state at the same time or in synchronism, and hence they will be having different propagation delay time and they are generating glitches. Thus, there is a possibility of the glitches occurring at the output of any decoding gates used with this counter. Thank you very much.